So section 1.5 should be easy if I do a decent job. Um, all the problems in section 1.5 have two terms, and in order to help you understand how these factor, I'm going to make up some problems that are inspired by what we're going to learn in section 1.5 that start off with three terms, and it might help us understand the concepts. So this is just a little bit extra. This is kind of a warm up. We'll do something that we know how to do, which will help us learn something we don't know how to do, or you might know how to do it, but just in case you don't. So warm up for section 1.5. Let's try to do some factoring. It's a nice review, but kind of an odd review. Let's factor x squared plus 0x minus 9. This is a trinomial, meaning it has three terms. It has not a number in front of the x squared term. For this, I'm going to cite factor. I'm not going to take the time to factor by grouping. What I'm about to do is I'm going to create my two parentheses. I'm going to split the x squared evenly between the two parentheses up front, and then I look at my signs. My signs in the problem are plus and minus. The numbers that I'm going to need to worry about are numbers that are plus and minus, big number plus, small number minus. To figure out what finishes up these parentheses, I'm going to need numbers plus and minus, big number plus, small number minus, that multiply to negative 9 and add to 0, because the negative 9 there is what I'm targeting. The 0 here I'm also targeting. Add in quotes because when the signs are plus and minus, the adding is really subtracting. So the numbers that multiply to 9, big number plus, small number minus, are 9 and negative 1, because 9 times negative 1 is negative 9. And 3 and negative 3, that's not really big number plus, small number minus, but because they're equal. But anyways, the best I can do when the numbers are tied. Both of those multiply to negative 9. Let me subtract these, or subtract these. If I add the 9 and negative 1, which is really the same as 9 minus 1, that gives me 8. That's not adding to 0. And if I work on the 3 plus negative 3, which is really 3 minus 3, that subtracts to be 0. So the pairs that I'm going to need are the 3 and the negative 3. And I'm just going to plug 1 in each parentheses, a plus 3 and a minus 3. I claim that I factored that correctly. I can go ahead and check this real quickly just to show you that it's correct. Let me multiply out x plus 3 times x minus 3. I'm going to multiply the x times x and get x squared. The x times minus 3 and get minus 3x. The 3 times x and get positive 3x. The 3 times minus 3 and get minus 9. The 3x's are opposites, they cancel, and that leaves me with x squared minus 9. So I know my answer is right. Let me do one more like this. Let me factor x squared plus 0x minus 16. Similarly, it's a trinomial. There's not a number in front of the squared term, so I can cite factor and not have to worry about grouping. Very specifically, I'm going to create my two parentheses. I'm going to load up the front with x's, and the ends, or the lasts, have to multiply to negative 16, have to quote add to 0. The factors of 16, negative 16 that I'm going to hunt around have to be the pair where the big number is plus, the small number is minus. And my choices would be 16 and negative 1, 8 and negative 2, 4, and negative 4, because each one of those have big number plus, small number minus, and if you multiply those, you're going to get negative 16. If I add these, if I do 16 plus negative 1, which is the same as 16 minus 1, plus a negative is the same as a minus, that would give me 15. If I did 8 plus negative 2, which is the same as 8 minus 2, that would give me 6. And if I checked 4 plus negative 4, which is the same as 4 minus 4, that would give me a 0. The numbers I'm going to need for my parentheses are 4 and negative 4. So I'm going to create my two parentheses, split the x's evenly between the first, and the numbers I get are positive and negative 4, and in either order. One parenthesis gets a negative 4, the other parenthesis gets a positive 4. So I've factored both of these correctly. And even though I've factored something with 3 terms, what I've really factored is something with 2 terms. The first example that I did, if I simplified it, that 0x isn't necessary. I factored x squared minus 9 realistically, because that 0x that means 0, and x squared minus 9 is the same as this. And similarly, the second problem, that 0x was a placeholder, and I really factored x squared minus 16. Had I written the problem factor x squared minus 9, well, because these two problems are equal to each other even though they look different, I can say x squared minus 9 factors into x plus 3 times x minus 3. Similarly, I could say x squared minus 16, which is the same as factoring x squared plus 0x minus 16 factors into x plus 4 times x minus 4. These two problems are one of the styles of problems that we're going to see in section 1.5. Very specifically, the versions of the problems with 2 terms without the zeros I call differences of squares. We're going to learn how to factor 2 styles of problems with 2 terms in section 1.5, and the easier is factoring differences of squares. So in section 1.5, all of the problems that are going to ask us to factor are going to have 2 terms. And there's 2 styles of problems. One of the styles is a difference of squares, which is a word I snuck in chapter P. Forget what section it was, but I put the word difference of squares in one of my groups of problems along. I snuck the word conjugate pairs in when I did that too, not that you'd remember that. But to be a difference of squares, you need to have this. You need to have 2 terms. Any letter or variable, which might be a nicer name, has an even exponent. Even numbers are 2, 4, 6, 8, 12, 14, and so forth. And any number is a perfect square, meaning I can take its square root and it comes out to an integer. So the kinds of letters that I might see, maybe an x squared, or I might see a y to the 4th, or a z to the 6th, or a w to the 8th. In order to classify as a difference of squares, those are the kinds of letters I might like to see. The numbers I might see would be 1, which is 1 times 1, 4, which is 2 squared, 9, which is 3 squared, 16, which is 4 squared, 25, which is 5 squared. This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. These are the perfect squares. So if I have this set up, if I'm given a problem with 2 terms, letters have even exponents, numbers are perfect squares, and there's a minus between, then that particular problem classifies as a difference of squares. The two simplified versions of the problems that I wrote before I jumped into this section, the x squared minus 9 and the x squared minus 16, fit these perfectly. There's two terms. When I get rid of the 0, the exponents are 2, which is an even number, and the numbers are perfect squares. These all factor, and they're super easy to factor. They all factor the same way. They all factor. The template is one parenthesis gets a plus, the other parenthesis gets a minus, and I fill up the parentheses by, I divide any exponent by 2, which we've done already, and I square root the numbers. And all of these I can sight factor. So if I asked you to factor x squared minus 16, nice and easy. I'm going to create two parentheses. One's going to have a plus sign, the other's going to have the minus. The exponent for the letter I'm going to divide by 2. So I'm going to go x to the 2 divided by 2 and get the letter for my answer. It's going to be x to the first. Because the x squared was written first, these x to the first are going to go up front. I have my signs in. The numbers I'd get by square rooting the number, not worrying about its sign right now. And if I square root 16, I get 4. One parenthesis will get a positive, the other gets a negative, and both of these would be considered correctly factored. Let me just write one more difference of squares, slightly more complicated. If I gave a problem like this, 25y to the 4th minus 9, this still classifies as a difference of squares in my mind. It has two terms, which is the first requirement. The letter y has an even exponent. It's an exponent of 4. And the numbers 9 and 25 are perfect squares. I factor perfect squares, super easy to factor. I create two parentheses. One parenthesis has a plus, the other has a minus. Any letter, I divide its exponent by 2. And so the y has an exponent of 4. Its exponent in the parentheses is going to be 2, and it's going to lead off the parentheses because the y leads off the problem. And any numbers, I'm going to square root. I'm going to square root 25, and I'm going to square root 9. On my calculator, there's a square root button. If I type square root and type in 25, I'll get 5. And if I do square root and type in 9, I'll get 9. So the square, 3 should I say. So the square root of 25 is 5. The square root of 9 is 3. The 25 is to the left of the y to the 4th, so the 5 that it turns into goes to the left of the y squared in both parentheses. The 9 is after the sign, so in the parentheses it goes after the sign. So this problem, 25y to the 4th minus 9, is going to factor into 5y squared plus 3 and 5y squared minus 3. That's not the same as 5y squared plus 3 squared. That would be a wrong answer, specifically because to write an exponent of 2, you have to have two identical factors. So that's one of the two styles of problems that we need to learn how to factor in section 1.5. The other style of problem is going to be a sum of squares, and let me write some sample problems real quickly and try to motivate this. If I asked you to factor x squared plus 0x plus 25, I can sight factor this. I know that ultimately I don't need any minuses in my problem, because if I've got a double plus, my factors are a double plus. This is a trinomial. I can ultimately sight factor it. I can split the x squared evenly up between the parentheses up front, and the numbers are going to have to multiply to 25 and add to 0. Now look at the factors of 25. 1 times 25 is 25. 5 times 5 is 25. The numbers that I put in the parentheses can't subtract to 0. They specifically have to add to 0. And 1 plus 25 is 26. 5 plus 5 is 10. Because I can't find a pair of numbers that do both, multiply to 25 and add to 0, I say that this is prime. Similarly, if I wrote a problem like this, x squared plus 0x plus 49, I should be able to sight factor this similarly. I can create two parentheses, split the x squareds evenly between the firsts, and then look for numbers that have to multiply to 49. They have to add to 0, and they need to be double plus. I can't introduce a minus in my factoring when the original problem was double plus. If I look at this, my choices for my numbers are 49 and 1. Those multiply to 49. 7 and 7. Those multiply to 49. If I add 49 and 1, I get 50. And if I add 7 and 7, I get 14. Because there's not a pair of numbers that do both, multiply to 49 and add to 0, this is also prime. So these are trinomials that reduce to binomials. This top problem on this sheet really is the same as x squared plus 25. And so if I asked you to factor x squared plus 25, you'd have to say that it's prime. And the second problem on this sheet is really the same as x squared plus 49. And if I asked you to factor x squared plus 49, you'd also have to say it's prime. These two problems, the versions of the problems that only have two terms, that's the other kind of problem that we get in this section. In section 1.5, we get difference of squares, and we get sums of squares. We did differences of squares. I kind of wrote what makes something a difference of squares on the other sheet of paper. Let me write what makes something a sum of squares. To be a sum of squares, you need to have two terms, and these versions of the problems have two terms. There needs to be a plus sign between, or an addition between the terms, which these have, as opposed to a subtraction or a minus between. The letters, again, have even exponents. Similarly, you might see an x squared, or I'll just do one letter, or an x to the 4th, or an x to the 6th, and so forth. And the numbers are perfect squares. The kinds of numbers I'd see: 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, and so forth. Sums of squares are actually easier to factor than differences of squares because all sums of squares are prime. So if I asked you to factor x squared plus 16, I'd look at this problem. It has two terms. there's a plus between, the letter x squared has an even exponent, and 16 is a perfect square, this guy's going to be prime. There's no way to factor that. Similarly, if I asked you to factor 25x squared plus 36, this has two terms, plus between, the letter x has an even exponent, and the numbers 25 and 36 are perfect squares. That makes this a sum of squares. All sums of squares are prime. So every problem in this section is either a difference of squares that has two terms, letters with even exponents, numbers perfect squares, minus between, and all difference of squares factor. They actually factor into conjugate pairs. They get two identical parentheses with opposite signs. If the problem is not a difference of squares, then it's a sum of squares, two terms, plus between, even exponents on the letters, perfect squares on the numbers, and all sums of squares are prime. So just a matter, when I go through the section to do the problems, it's just really a matter of identifying whether I'm dealing with a sum of squares or a difference of squares, and then using the technique to factor for the difference of squares, and then writing prime if it's a sum of squares. If I look at problem 2, it lives in the difference of squares moment because it has two terms. The letter x has an even exponent. 81 turns out to be a perfect square. I'll show you that real quickly on my calculator, and there's a minus between. So I claim that this is a difference of squares because it fits the criteria. Two terms, minus between, letter with an even exponent, numbers a perfect square, and numbers are perfect square if when you square root them, you get a nice integer. So this is going to factor. I'm going to take the exponent on the y and divide it by 2 and get y to the first. And I'm going to square root the number and get a 9. And then when I factor differences of squares, I get two identical parentheses, and I just split the letters evenly into both parentheses and the number evenly into both parentheses. Number 2 is going to factor into either y plus 9 and y minus 9, or if you prefer, y minus 9 times y plus 9. Number 4 turns out to be a sum of squares. It's a sum because of the plus. It's a square because it has two terms. The letter has an even exponent, and the number 81 is a perfect square. 81 is 9 squared. Sums of squares are all prime. Problem 6 is a difference of squares. It has a minus. So I'm going to figure out what goes in my parentheses. For the letter, I'm going to divide its exponent by 2, and the number, I'm going to square root it. Not that you can see. Sometimes when the lighting gets funky in here, I can't see, but the square root of 49 is 7. Because it's a difference of squares, I get two parentheses. One has a minus, the other has a plus. It doesn't matter if your minus is in the first or the second parentheses. And then I fill up the contents exactly the same. The b's started first, so they go in the first position. The 49s ended, so the 7s that turn into finish up. So that could be an answer. Equivalently, the answer could be b plus and b minus 7. Problem 8 is a sum of squares. It's a square because it has two terms. The exponent is even. The number is a perfect square. The plus between makes this prime. All sums of squares are prime. All differences of squares factor. Ten's a difference of squares. The minus makes it a different. It's a square because the exponent on the letter is even, so I'm going to divide its exponent by 2. And the numbers are perfect squares. I'm going to square root the 16 and square root the 49. If when I square root the numbers I get a nice integer and not a decimal, I'm dealing with a good number. So let me square root 16, and the square root of 16 is 4. And then I'll square root 49, and the square root of 49 is 7. So I'm going to create two parentheses. One has a plus sign, the other has a minus. The b's are going to be up front because they come from the first term. The 4 that came from the 16 is going to go up front because it came from the piece to the left of the minus sign. After the signs are what the 49 turns into, which is a 7. And I'm going to get two parentheses, one with a plus, one with a minus. They're identical. These are actually conjugate pairs. When you get identical binomials in parentheses with opposite signs, we call those conjugate pairs. So it would be proper to say differences of squares factor into conjugate pairs for what that's worth. 12 is a sum of squares. It's still a square problem because it has exactly the same 16b squared and the 49. The plus makes it prime. 14 is probably a difference of squares. As long as I can square root the numbers and divide the exponent by 2 of the letter, not get a fraction, it's going to be a square problem. The minus makes it factorable. So I need to square root, make sure the numbers are square rootable. If either number wasn't square rootable, then it wouldn't be factorable. But they both are. If I square root 81, I get 9. And if I square root 25, I get 5. So I'm going to create my two parentheses. I'll flip the signs. I'll make the first one minus, the second one plus. It doesn't matter. You just need one parenthesis with a plus, the other with a minus. The x is going to precede the signs because the x squared preceded the signs. The 81 turns into a 9 that's going to precede the x because the 81 preceded the x, the 9 should. The 25 came after the signs, so the 5 should be after the signs. And your answer can be flip-flop from this. You could have the plus 5 first and the minus 5 second. 16, a sum of squares. It's a square because the letter has an even exponent. 81 and 49, if you square root them, they're perfect square roots. The plus between makes it a sum of squares. And all sums of squares are prime. The next chunk of problems have some common factors, and maybe I'll make a part 2 to this video because we're at 28 minutes already, and I probably have another 20 minutes or so, maybe 25, and probably better to pause it and make a second part.